Hello Matadors, 8th grade science students. We've been learning about waves and we are currently in wave interactions. Last we left on Friday, some of you were able to do this investigation on It's All Material. There is a video in McGraw Hill. If you watch that video, it shows some different scenes around, and all I want you to do is watch those different scenes. We've got a music room, a hallway, a cafeteria, and a regular classroom where the kids are reading silently. And all I want you to do is write down your observations as to how you think the sound is bouncing off the different surfaces. You can use words that we just recently learned, like reflection, or even looking at some of the words absorption or transmission, where it goes into the surface or it goes through the surface. Any of those are great. And your notes, we should have already filled in for reflection. Here is what we have already done for reflection. Now you have to write in your own examples. I'm not writing those in for you. And then we did for absorption, okay, where we see that the energy is going in, but it's just being absorbed by the surface. And once again, you write down some examples of absorption. And then we also did transmission, where we had the energy coming in. Some of it gets absorbed, but some of it also goes through to the other side. And this can be through a medium of solid, liquid, or gas. Okay. The next one that we're doing is, if you after your investigation, go ahead and turn the page and go ahead and you want to answer the question, how does the type of material affect how it will be used? This is kind of difficult just based on the It's All Material. So what I would recommend that you do is read this music connection that talks about acoustic engineers and how they take into account the type of materials that they're working with. If they're designing a concert hall, these engineers carefully choose the shapes and the materials to control sound waves. Stages, the stage has a wooden floor to improve vibrations. The curved panels on the ceiling reflect sound waves in different directions to fill the space. So if you have very bad seats at a concert, don't worry, because if it was engineered correctly, the sound will get to you. Also on highway, sound barriers, that's this picture right here. That's another example of controlling sound waves. The barriers often are made from wood, concrete, or metal, like the one shown on the right, and the barrier's purpose is to keep the highway noise away from residential areas, away from your house if you live near a freeway. The higher the wall, the more the sound will be reflected from the hard surface and back onto the freeway. The next thing I'd like you to do is, it says when a wave interacts with matter, it can reflect energy, or it can absorb the energy, or it can transmit the energy, or do all three. Develop a model using this figure below right here to show me how sound waves interact with the materials in the room. So we've got a speaker here. So how's the sound going to get to this man's ears? We've got some carpet, we've got some hard walls. Can you draw some arrows here showing me how the sound is interacting? And you can go ahead and write your response. It says in your science notebook, but just do it right here or right here. This is your science notebook. So just write it on the sides, and you can draw arrows showing and label the arrows showing if it's reflecting, transmitting through certain surfaces like this soft chair. And so that's what the 3D model is for. The next page that we're going on to is the life science connection, showing how the anatomy of an ear actually works. So just read this. It's just very interesting information. The last thing I want you to do is go back to your CER and write in evidence A. I'm going to go back to right over here. So if you go back to page 38, where it says evidence A, I want you to tell me, how does a wave travel through matter? How does it reflect, how does it absorb, and how does it transmit? Okay, so that's what you want to do on page 38. Okay? And that is what we're doing. And our next section is we're going to talk about how a wave travels through matter, but I'm going to start a new video for that. Remember back looking at our phenomenon on why are the walls of a recording studio covered with foam? And not just foam, but we've got carpet here, and the foam is different shapes. It's very odd sizes. So as we move into the next section, which is what affects how a wave travels through matter. We just talked about reflection, absorption, and transmission. And we're asking, do all the waves interact the same way? Considering how quickly a water wave at the beach comes to shore, think about how a car horn can be heard almost immediately, really fast. What would happen if you place something between you and the microphone in a recording studio? So our next lab that we're going to do is the echo. Now if you have a place, an open place at home that you can do this, that would be great, because all you need is you just need a meter stick or a tape measure and some sort of a stopwatch, and maybe somebody to help you out. So you want to measure a spot 30 meters from the wall, clap your hands once and listen for the echo. Now try and clap in time with the echo, and if you hear the echo after each clap, then you need to clap faster, because you want to be clapping at the same time as the echo. And you want to try and match that echo speed. Once you've matched it, then you want to start your stopwatch and measure each time you clap 25 times. You want to follow along with this table so you can see how much time it takes to clap 25 times. So I know 50 meters is a pretty far distance. So if you can go outside, if your parents will let you go outside in a place where you're around nobody else, you can find a place and measure this out. So you want to be up against a wall though, so that there will be an echo. And you just kind of tell me how much time it takes to do 25 claps. Okay, so 30 meters away, 40 meters away, and 50 meters away. And you'll see what will happen the further away you go, what's happening to that echo speed. And if you want to do this multiple trials at each of the distances to get kind of an average, that's definitely a great thing to do, getting averages. So what you want to do, come over here, is once you get your data, you want to calculate the speed of sound. And the speed of sound can be calculated by dividing the distance by the time. So here's the formula for speed. We use V because it stands for velocity. And you can do it like this, or we can switch the places around the equal sign. And so we have our 30 meters, our 40 meters, and our 50 meters. And so you need to fill in the time, and then just divide those, and that'll get you your speed. Now, if you were to perform this experiment on a colder day, the speed of the echo would be slower. Why is that? Why would the speed of sound be less on a colder day? So that is the lab echo. Hopefully you guys will be able to do that. If not, I'll try and see if I can do it so you guys can at least get some data. But no guarantees. It's best to do it on your own. All right. Hello again, class. We just finished our lab on echo. So you were seeing what the echo speed was at different distances. Now we're moving down into the speed of sound. So in the lab echo, you hopefully were able to calculate the speed of sound through air. Now recall that for sound to be transmitted, energy has to pass from particle to particle. The material or medium that the sound passes through affects how fast the sound moves. So two factors that influence the speed of sound are density and temperature of the medium. Now, gas particles are far apart and collide less often than the particles in a liquid or solid. As shown in this table on the right, a gas takes longer to transfer sound energy between particles. In a solid where the particles are very packed close together, the particles collide and transfer energy very quickly. The more dense a medium, the faster sound will travel through it. Particles move faster and collide more often as the temperature, so here's our other factor, temperature of a gas increases. This increase in the number of collisions transfers more energy in less time. Temperature has the opposite effect on liquids and sounds. As liquids and solids cool down, the molecules move closer together. They collide more often and transfer energy faster. So we're going to use this information to fill in some of our awesome booklet. So here we had speed of waves. I'm going to flip, we haven't gotten to diffraction yet, so I'm going to skip to speed of waves. And we just did this one with our echo lab. So distance in meters divided by time is our speed in meters per second. So you can put that one down for speed of sound. But here we go to I'm going to use this information to complete this. And you guys, I'm going to hold this on here right here. So for sound to be transmitted or moved, it has to go from one particle to another. So this depends on what type of medium it is. Is it a solid, a liquid, or a gas? It depends on the density, how close together it is, and also depends on temperature. So here we have density. If it's a gas, gases have low density, meaning they're really far apart, okay? And this transmits very slowly. It takes a while for them to hit each other. This is why they put gases in between window panes, so that any sort of energy or heat can transfer slowly through those panes. Now solids, these are very high density because all those molecules are very, very close together, and so waves will travel very quickly. Now speaking of temperature, down here, if a gas has a very high temperature, then they're very excited, and these are, even though they're far apart, they're going to move very, very quickly because they're so excited with this high temperature and heat. They have lots of energy. High heat equals lots of energy, and they'll travel faster. Now on the opposite, these are the opposite of a gas. When they cool down, that's when it actually travels faster, when a liquid cools down. And when a solid even cools down and gets really, really cold, that's when it's going to actually be much, much faster. And that's speed of sound. All right, class, our next vocabulary word is diffraction. Now this is on page 50. It's after a lab breaking waves, but we're not going to do that. Go ahead and skip this lab breaking waves. Just skip it and go straight to reading about diffraction. The waves in breaking waves, if you would have seen it, they didn't break, but rather they changed direction when it came to a barrier. That was if we put a space in the barrier. The change in direction of a wave when it travels to the edge or even through an opening is called diffraction. Both water waves and sound waves diffract. You've experienced sound diffraction if you've ever been in the hallway and you can hear people talking in a room before you even got to the open door of that room, because that sound goes around the corner and travels to your ear. Diffraction causes water waves to travel around the edges of the object and spread out after they travel through the opening. Just like in your breaking waves lab, had we done it in class, there was more diffraction occurring as the size of the object or opening becomes similar in size to the wavelength of the wave. So that's diffraction, and we're going to move over to our little booklet here and see where diffraction is. We're going to go to that flap. We're going to open it up, and here we have some cool pictures. I already have the definition there for you. This only happens with water waves and sound waves, so make sure you put those down. You were given some examples in the book, and here we have, it's hard to see, but there is an object there. So we see that the wave is bending around an object, and that object's right there, so it kind of bends around that object. And here we have an opening, and so we have a wave bending after the space. So it's going to go through this space, and then it's going to bend to the sides there. And here we have diffraction increases as the object or opening becomes similar to the size of the wavelength. Okay. The last thing we have to do is a 3D thinking on this page. Once again, we're on page 50. And so imagine you're conducting a new ripple tank experiment instead of the breaking waves one that we did. And we have two different barrier structures. The first time you make the waves, the structure is a sponge. Now you guys were here when we did see the first time we did the breaking waves lab. The second time it's a brick, solid brick. Based on your previous observations, create an argument for which structure you think will have the most effect on frequency, amplitude, and wavelength. Now this you'll have to think back to lesson 1 when we're talking about wavelength, amplitude, and frequency. Okay, frequency is how many waves are passing per second. Amplitude is the height of the wave, and wavelength is the length from top of the wave to the top of the wave. And when we're talking about water waves, and for this one, because we're talking about a ripple tank, we are talking about water waves. Okay, so just kind of give me an argument about choose which one, the sponge or the brick, will have the most effect on frequency, amplitude, and wavelength. And I want you to write that right here. If you don't remember about frequency, amplitude, and wavelength, go back to lesson 1 or look at your foldable that we did for those. Then you want to go back to your CER and record your evidence on evidence B. So I'm going to flip back to page 39. And here we have more evidence, evidence B. What evidence have you discovered to explain how wave interacts with matter? So we're going to talk about the different speeds and tell me how it interacts with different mediums. That's solid, liquid, and gas. And then once again, what is diffraction? What is that bending? Okay. When you finish that, go ahead and go back to tell me why you think recording studios now have foam on the walls. Why? Why do you think they have foam on the walls? Hopefully you have a better idea about why that is. And then you want to come down to your reasoning and make sure you're giving me 3 to 5 complete sentences. By 8th grade, you should be able to write a complete sentence and give me evidence that should be from here and here explaining why you think recording studios have foam on the walls.